So we're going to continue on the notes. This is part 3 of the chapter 8 notes, except on computer. Oops. Sorry. Let me get back to the right spot. So here we are. Okay, so the next thing is about something called effective nuclear charge. The effective nuclear charge is the positive charge felt by an electron. And so just as a quick reminder, we have the nucleus in the center, and you have of the atom, and you have the electrons that are orbiting around it in different shells, subshells, etc. So the stronger the effective nuclear charge, that means the electron feels like it's being pulled in towards the nucleus greater. So the stronger the effective nuclear charge, the positive charge felt by electron, the more that it's being pulled towards the nucleus. And in general, that also means that the atom would be smaller, okay? So if it's being pulled, it's like attracted to the center. Like if the Earth was being pulled to the sun closer, stronger, then it would probably be a bit closer to the sun, okay? If the gravitational force of the sun were greater, okay, like somehow it magically gains a lot more mass. That's not happening, but if it magically somehow gains more mass, then the sun will pull the Earth in stronger, and it'll probably pull it in a little bit closer. Earth's orbit will be a little bit closer than what it is. Okay, so that's kind of definition of effective nuclear charge. There is an equation, but we don't really have to know it, so complicated. Effective nuclear charge is pretty much just, it's approximately, I'm not going to even bother with that top equation, Z, which is the atomic number, minus the outer or inner core electrons. So atomic number, just a number on the periodic table. Sodium is atomic number 11, magnesium atomic number 12, aluminum atomic number 13, silicon atomic number 14. Okay, so the core electrons, though, is really the shell before it. So let me get back to, I'll look at a periodic table. Sodium, magnesium, aluminum, silicon. So periodic table, oh, this is kind of one. So sodium's here, magnesium, aluminum, silicon. Atomic number 11, 12, 13, 14. So the core electrons is the shell before it, which is really the noble gas before it, which is neon. The shell before it, neon, which is atomic number 10. So the core electrons before it, because this is the n equals 2 shell. Here, this is n equals 3, 3s1. This is the third shell. First electron, third shell. Second one. And in the p subshell, but third one, fourth one. But the core, inner core electrons is the second shell of electrons, or in this case, neon is 10. It's the noble gas before it. Okay, let me get back to where we were. Here we go. So the noble gas before it, or the core electrons, inner core electrons, really the noble gas before it, is just, was 10. So Z minus number of core electrons, 11 minus 10, 1. 12 minus 10, 2, 3, 4. Okay, so notice that as we go across the periodic table then, the effective nuclear charge actually increases. Effective nuclear charge increases. Because of this, we'll get to where this number comes from later. Notice the radius actually decreases. So as I go across the periodic table, the radius of an atom decreases. So we're going to get to that in a second, the radius itself. But as I go across the periodic table, we're right now just looking at the representative elements. But as I go across the periodic table, the effective nuclear charge increases. Not getting to it right now, but also the effective nuclear charge increases as I go up a periodic table. Okay, I just mentioned radius, so I just want to get to it now. Radius of a circle, you already know, from the center to, you can say, the edge or whatever, okay? The thing is, this is not an actual good depiction of how atoms are. They are not, when there are two atoms and they're sharing electrons or even bonded together, they are not touching each other at single points, also known as tangents. This is not reality. This is how they actually are. Okay, when they're sharing electrons, they're almost like melted into each other, you can say. So how do we define the radius? And another problem is there is no top layer. It's not like, well, there's a specific outer edge. Because these electrons are buzzing around, floating around different shells, these things, there is no like, well, it stops right here. It's kind of like there is no top of the atmosphere. It's not like, well, you see where the top of water is, above the water you can breathe, below the water you can't breathe if in a swimming pool. It's not like that with air. Like, below the atmosphere you can breathe, in space, and right above it, it's not like a line like that. Right above it, there's no air and you die. As you go up higher and higher in space, there's going to be less and less and less air until it's practically none. So as a spaceship goes up into space, there's just less and less and less and less and less air until there's pretty much no more air up there. So the chances of finding nucleus is not there is no specific line. It's just going to be less and less and less chance of you finding it there as you get further away from the nucleus. So how do we define the radius then? We define a nucleus as half the distance between the nuclei of a diatomic molecule. Diatomic means 2 atom. Okay, so that's what the textbook defines as half the distance between the nuclei. So, well, you can imagine here, half the distance between the centers of 2 atoms in a diatomic molecule. So that's how we define it. Well, we just said, hey, effective nuclear charge increases up and to the right. And as effective nuclear charge increases, 1, 2, 3, 4, the radius decreases. So it should be the opposite of this. As effective nuclear charge increases up and to the right on the periodic table, the radius should decrease as we go up and to the right in the periodic table. So here are the actual numbers of atomic radius of our elements. These are just the representative elements on here. And those transition metals are not on here, but the same rules still apply for even transition metals. Okay. Notice the trend it's called the trends, atomic radii trends. It increases left and down on a periodic table. So atomic radius increases left and down on a periodic table. The element that's first left and down on a periodic table would be the largest one. Conversely, up and to the right is smaller. These are general trends. This is not for every single one. In fact, you could see lots of exceptions. So notice it increases going to the left. 98, 99, 127, 128, 132, 143. Yay, it increases going to the left. But there are exceptions, like here, 114, 140, 139, 137, 135. It actually decreased a bit. Okay, yes, that's an exception. But the overall pattern, okay, the general trend is that it increases left and down on the periodic table. As I go down any group on the periodic table, the trend is, if you see patterns, hey, it looks like it gets bigger as you go down any group. It looks like as I move to the left, it gets bigger. Or you could conversely say, as I move to the right, it gets smaller. Is that the case for every single one? No. That's not the case for every single one. But overall, increases left and down. So that's why these are also known as general trends. There are, I believe, 4 or 5 periodic trends that you're going to know. And this is one of them. Atomic radius increases left and to the right. So if you're just given a regular periodic table, not this one, and you're like, hey, which is bigger? Rubidium, potassium, gallium, or indium. Okay? Between rubidium, potassium, gallium, or indium, you're like, well, I know it increases left and down, so rubidium would be the biggest. If the question is which is the smallest, rubidium, potassium, gallium, indium, well, I know it increases left and down, so the smallest must be the one that's higher up and to the right, which would be gallium. So normally you wouldn't be given a periodic table like this. Let me go back to, say, this periodic table. And a question could be between aluminum, boron, carbon, silicon. Aluminum, boron, carbon, silicon. Which of these 4, aluminum, boron, carbon, silicon, is the largest? Well, you should know, increases left and down. So aluminum is the largest. Of these 4, aluminum, boron, carbon, silicon, which is the smallest? Well, you should know. Increases left and down, so the smallest will be the one that's higher up and to the right, which would be carbon. So that would be the trend, increases left and down. Go back to that slide. Increases left and down. So here are the numbers again. Aluminum, boron, carbon, silicon. Aluminum would be the biggest, and of these four, carbon would be the smallest. Could it actually have been one of the exceptions? Yes, it could have been. And I wouldn't exactly know without looking at this table, but based on the general patterns. Okay, so that's these trends. If you want to know, are you really sure it's the biggest? Are you really sure it's the smallest? Okay, well, maybe I don't exactly know, but I can look at the actual numbers if I really needed to. But according to the overall patterns, okay, I see this. So that's general trends. There will be several general trends. This is actually one of the more clear general trends. Okay, if you were to graph atomic number versus radius, this is what you'll see. Where lithium, sodium, potassium, rubidium, cesium are at the top. Lithium, sodium, potassium, rubidium, cesium are at the top. At the bottom, okay, noble gases weren't on that, I don't think. Yeah. So fluorine, chlorine, bromine, iodine, acetine, though technically noble gases are smaller, but fluorine, chlorine, bromine, iodine, okay, are the smaller ones. So notice there's all these weird exceptions. Shouldn't say weird, but you know, there's some exceptions there where it's like, okay, it's not exactly a perfect trend, but overall, there's a pattern, is the point. It's, if it was all random, these points would be all over the place. They wouldn't make any sense, okay? So if there was no pattern, this would just be all over the place. But there is a pattern to this. So that's atomic radius. Okay, how does atomic radii compare to ionic radii? So here is our neutral atom, and here it's positive ion. Radius in the y-axis. Notice lithium ion smaller than regular lithium. Sodium ion smaller than regular sodium. Potassium ion smaller than regular potassium. Rubidium ion smaller. You get the point. So the positive cation, notice, is in general smaller than the neutral atom. What if we're talking about anions, negative? Regular neutral atom, anions. Again, radius is the y-axis. Fluoride ion, chloride ion, bromine ion, oxygen, that's not oxygen, iodide ion is bigger than its neutral atom. So if it loses electrons such that it becomes positive, it gets smaller. If it gains electrons such that it becomes negative, it gets bigger. In fact, that's a general rule. Cations, which are positive ones, cations are always smaller than the atom from which they formed. Anions are always larger from the atom from which they form. In fact, the charges is actually, maybe I should have worded it, cations are always much smaller than the atom from which they form. Anions are much larger from the ions from which they form. This is actually somewhat to scale. Lithium, lithium ion. Fluorine, fluorine ion. So when it gets smaller, it gets a lot smaller. When it gets bigger, it gets a lot bigger. Here's the charges of ions. I'll move my face. Remember, group 1, positive. Group 2, positive 1, group 1, positive 2, group 2. Aluminum group, positive 3. Halogens, negative 1. Oxygen group, negative 2. Nitrogen group, negative 3. So the negative ones get much bigger. The positive ones get much smaller. You can even see the general sizes. In general, the negative ones are a lot bigger. So if you're going to compare sizes of ions, negative ones, in general, are going to be big. Yes, fine, like cesium. It's a pretty big positive one. But in general, negative ones big, positive ones small. Within the positive ones, notice the increase is going down and to the left. Within the negative ones, increase is going down and to the left, just like it was for the regular atomic radius. Okay, so I think we will just pause for here for now.